questions are already emerging across northern South America and the wider Caribbean as seismic monitors piece together one of the region's most extraordinary earthquake sequences in recent history. Why did two powerful earthquakes occur only 39 seconds apart? Did the first rupture set the stage for the second? What does this rare seismic doublet reveal about one of the most active plate boundaries in the Americas? As emergency assessments continue and scientists refine the data, the answers are beginning to paint a clearer picture of an event that unfolded with remarkable speed along Venezuela's northern tectonic frontier. A powerful earthquake sequence struck northern Venezuela late on the 24th of June, producing two major earthquakes separated by only 39 seconds. The sequence began with a magnitude 7.2 earthquake at approximately 4 minutes past 10 in Coordinated Universal Time, followed almost immediately by a larger magnitude 7.5 earthquake at approximately 5 minutes past 10 Coordinated Universal Time. The epicenters of both earthquakes were located southeast of Yumare in Yaracuy State, placing the ruptures near one of the most complex and active sections of the plate boundary between the Caribbean Plate and the South American Plate. According to information released by the United States Geological Survey, the first earthquake occurred at a depth of approximately 12.5 miles, or 20.3 kilometers, while the larger second event originated even closer to the surface at a depth of roughly 6.25 miles, or 10 kilometers. Although the difference in depth may appear modest, both earthquakes were shallow enough to produce strong shaking across a broad region, increasing the potential for structural damage compared with deeper earthquakes of similar magnitude. The sequence was immediately recognized as a seismic doublet, a relatively uncommon phenomenon in which two earthquakes of comparable size occur close together in both time and location. Unlike the more familiar pattern of a single large earthquake followed by progressively smaller aftershocks, a doublet consists of two major ruptures capable of generating significant shaking on their own. In this case, the first magnitude 7.2 earthquake served as the foreshock to the larger magnitude 7.5 mainshock that followed only 39 seconds later. That brief interval transformed the event into something far more significant than an ordinary earthquake sequence. During those 39 seconds, the crust beneath northern Venezuela had not yet settled from the initial rupture before another, even larger section of the fault system failed. Instead of dissipating stress entirely, the first earthquake appears to have been followed almost immediately by a second rupture involving an adjacent or connected portion of the regional fault network. The earthquakes occurred near geographic coordinates of approximately 10.435 degrees north latitude and 68.472 degrees west longitude, an area situated inland from Venezuela's north-central Caribbean coastline. Although the epicenter lies southeast of the town of Yumare, the broader tectonic setting extends across much of northern Venezuela, where several major strike-slip fault systems accommodate the continuous movement between two enormous tectonic plates. The Caribbean Plate moves eastward relative to the South American Plate at an average rate of roughly 3/4 of an inch each year, or about 20 millimeters annually. That movement may seem almost insignificant over the course of a single year, yet across decades and centuries the accumulated strain becomes immense. Rocks locked together along faults resist movement until stresses exceed their strength. When that threshold is finally crossed, stored elastic energy is released almost instantaneously, generating seismic waves that radiate outward through the surrounding crust. The plate boundary across northern Venezuela differs substantially from the subduction zones responsible for many of the world's largest earthquakes. Rather than one tectonic plate diving beneath another, this region is dominated primarily by horizontal motion. The Caribbean Plate slides eastward past the northern edge of South America in a right lateral strike-slip system. In practical terms, if an observer stood on one side of the fault and looked across it during movement, the opposite side would appear to shift toward the right. This style of faulting bears strong similarities to California's famous San Andreas Fault, although the Venezuelan system possesses its own unique network of interconnected structures. The earthquake mechanism determined for the magnitude 7.5 event aligns closely with right lateral strike-slip movement, reinforcing long-standing geological understanding of the region. Based on the earthquake's location, focal mechanism, shallow depth, and the regional tectonic framework, the most likely source of the rupture is the San Sebastián Fault, or one of its closely related branches within the broader Bocono-San Sebastián El Pilar fault system. This extensive fault network stretches for approximately 800 miles, or about 1,300 kilometers, across northern Venezuela, and serves as the principal boundary accommodating motion between the Caribbean and South American plates. The San Sebastián Fault itself extends for more than 185 miles, or over 300 kilometers, generally following an east-west orientation parallel to Venezuela's northern coastline. Geological studies indicate that this fault accommodates movement at a rate of approximately 7/10 to nearly 9/10 of an inch annually, equivalent to roughly 18 to 22 millimeters each year. Although such rates appear slow in human terms, they represent substantial tectonic motion over geological timescales. Near the epicentral area southeast of Umare, the regional geology becomes especially intricate because multiple major fault structures converge within a relatively confined area. The Bocono Fault, one of Venezuela's most significant strike-slip faults, trends generally northeast to southwest through the Venezuelan Andes before approaching the Yaracuy Valley. Nearby, the San Sebastián Fault branches toward the Caribbean coast, while additional offshore splays continue beneath the adjacent marine basin. The Oca Ancon fault system also contributes to the broader regional deformation farther north. Rather than behaving as isolated fractures, these faults interact mechanically over long periods. Stress transferred along one segment may influence neighboring faults, increasing or decreasing the likelihood of future movement depending upon the evolving stress field. Such interactions help explain why large earthquakes sometimes occur in clusters or sequences, rather than as completely independent events. The extraordinary timing of the June earthquake sequence has therefore attracted particular attention. A separation of only 39 seconds strongly suggests that the initial rupture altered stress conditions rapidly enough to facilitate failure along another connected portion of the fault system. While detailed finite fault models will continue refining the exact rupture process, the available observations already indicate a complex interaction involving more than a single isolated fault patch. Earthquakes of this magnitude also occupy much larger areas than the single dots typically displayed on seismic maps. Epicenters represent only the point on Earth's surface directly above where rupture begins. The actual fault movement extends far beyond that location. For a strike-slip earthquake approaching magnitude 7.5, the ruptured fault surface commonly spans approximately 93 miles in length and around 12 miles in width, corresponding to roughly 150 kilometers by 20 kilometers. Within that broad zone, opposing sides of the fault may shift by several feet, releasing energy accumulated over many decades. This distinction is important because communities located considerable distances from the mapped epicenter may nevertheless experience intense shaking if they lie above portions of the ruptured fault plane. Strong seismic waves also propagate efficiently through competent crustal rocks, allowing shaking to be felt across much of northern Venezuela and neighboring countries surrounding the Caribbean basin. The shallow depth of the mainshock further increased the efficiency with which seismic energy reached the surface. Deep earthquakes lose more energy before their waves arrive at populated areas, whereas shallow events concentrate much of their energy closer to the ground surface, where buildings, transportation corridors, utilities, and other infrastructure are located. At approximately 6¼ miles, or 10 kilometers below the surface, the magnitude 7.5 earthquake occurred well within the depth range commonly associated with damaging crustal earthquakes. Although immediate reports focused on the earthquake magnitudes and locations, the geological significance extends beyond the numbers themselves. The epicentral region occupies one of the principal transform boundaries in the Western Hemisphere, where continuous tectonic motion has shaped northern Venezuela's mountain ranges, valleys, coastal plains, and offshore basins over millions of years. The same forces responsible for building these landscapes continue operating today, accumulating strain along faults that periodically release energy through major earthquakes. Northern Venezuela has experienced destructive earthquakes throughout recorded history. reflecting the persistent activity of this plate boundary. Yet despite its well-established seismic hazard, earthquakes exceeding magnitude 7 remain comparatively infrequent. Historical records indicate that only a limited number of earthquakes reaching or exceeding that threshold have occurred along northern Venezuela, or immediately offshore, since the beginning of the 20th century. That rarity makes the June doublet especially notable, not only because of the size of the mainshock, but also because it followed another major rupture by less than 1 minute. The immediate vicinity surrounding the June earthquakes has also experienced relatively few large earthquakes during the past century, compared with many other active plate boundaries worldwide. Within approximately 155 miles or 250 kilometers of the epicentral area, only a handful of earthquakes of magnitude 6 or greater have been documented over the last 100 years. Even so, the historical record demonstrates that the region is fully capable of generating damaging earthquakes when accumulated tectonic stress is finally released. The area's recent seismic history already hinted that strain remained active within the broader fault network. During September of the previous year, another notable earthquake doublet occurred to the southwest of the current epicentral region. Those earthquakes measured magnitude 6.2 and magnitude 6.3 and caused widespread structural damage across portions of Zulia and Lara, resulting in casualties and injuries while underscoring the continuing activity of northern Venezuela's interconnected fault systems. The earthquakes of September in the previous year were not isolated reminders of regional seismicity. They formed part of a much longer pattern extending back generations, illustrating that northern Venezuela has repeatedly experienced destructive earthquakes as strain accumulates along the Caribbean-South American plate boundary. Historical records document several significant earthquakes affecting the same broad region, each adding another chapter to the geological history of a landscape that is continually reshaped by slow but relentless tectonic motion. Among the better documented modern events was the magnitude 6.4 earthquake of September 2009, centered northeast of the June 26 epicentral area near Moran. That earthquake injured dozens of people and damaged numerous buildings, serving as another reminder that even earthquakes below magnitude 7 can inflict considerable impacts when they occur at shallow depths near populated areas. Earlier still, a magnitude 6 earthquake during the late 1980s caused structural damage in the Valencia region, while a magnitude 6.1 earthquake farther west during the mid-1970s affected communities along the same broad tectonic corridor. The most devastating earthquake in the surrounding region during the modern instrumental era remains the Caracas earthquake of July 1967. Measuring magnitude 6.6, that earthquake struck approximately 81 miles, or 131 kilometers, east of the June 26 doublet. Despite being smaller than the recent magnitude 7.5 mainshock, its proximity to densely populated Caracas contributed to catastrophic consequences. Hundreds of people lost their lives, many more suffered injuries, numerous apartment buildings collapsed, and widespread destruction altered parts of the Venezuelan capital. The event demonstrated that earthquake magnitude alone does not determine disaster potential. Population density, construction practices, local geology, and proximity to the rupture all influence the severity of the outcome. Since the beginning of the 20th century, northern Venezuela and nearby offshore areas have experienced only a limited number of earthquakes reaching magnitude 7 or greater. That relative infrequency often creates long intervals during which stress quietly accumulates beneath the surface. Unlike regions where moderate earthquakes occur regularly and release portions of the stored strain, major strike-slip faults can remain locked for decades before producing abrupt episodes of large displacement. The June 24 sequence therefore stands out not merely because of the magnitude of the mainshock, but because of the remarkable manner in which the earthquakes unfolded. Seismic doublets of this size are uncommon worldwide. Most large earthquakes produce aftershocks that are substantially smaller than the principal event. In contrast, this sequence consisted of two earthquakes separated by only 39 seconds, with the first measuring magnitude 7.2 and the second increasing to magnitude 7.5. That distinction carries important implications for understanding the rupture process. Earthquakes begin when stress exceeds the strength of rocks along a fault. Once rupture starts, it propagates rapidly across the fault surface at speeds approaching several miles per second or several kilometers per second. In many cases, the rupture eventually slows and stops after releasing much of the accumulated strain. During a seismic doublet, however, the first rupture appears to alter stress conditions sufficiently to encourage failure on another adjacent section before the crust has time to stabilize. Rather than representing two completely independent earthquakes that merely happen to occur close together, the June sequence likely reflects an interaction between neighboring fault segments within the same regional deformation zone. The first rupture may have transferred stress into an adjoining locked section, promoting almost immediate failure there. Because the interval between earthquakes measured only 39 seconds, there was little opportunity for the crust to return to equilibrium before the second rupture commenced. The precise geometry of that interaction will continue to be examined as additional seismic records, satellite observations, and geodetic measurements become available. High-resolution analyses can reveal where rupture initiated, how it propagated across the fault surface, and whether multiple fault segments participated during the sequence. Such studies frequently require weeks or months of detailed processing before a complete picture emerges. Even so, the currently available information already aligns closely with rupture along the San Sebastián Fault or one of its associated branches. The epicentral coordinates place the earthquakes near the transition between several major mapped faults that collectively accommodate the eastward motion of the Caribbean plate. That network has developed over millions of years as the two tectonic plates have continued sliding horizontally past one another. Unlike mountain-building collisions where crust is compressed and uplifted, strike-slip systems primarily accommodate sideways displacement. Rivers crossing active faults gradually become offset. Valleys may shift position through repeated episodes of fault movement. Linear ridges, elongated depressions, and aligned stream channels often preserve evidence of repeated earthquakes spanning thousands or even millions of years. The Yaracuy region illustrates this relationship particularly well. The surrounding landscape reflects prolonged deformation associated with the interaction of the Bacono Fault, the San Sebastián Fault, and additional link structures extending toward the Caribbean coast. Although erosion and vegetation conceal many portions of these faults, geological mapping reveals their influence across much of northern Venezuela. The Bacono Fault extends through the Venezuelan Andes before approaching the Yaracuy Valley, where deformation becomes distributed among several interconnected structures. The San Sebastián Fault continues generally east to west, roughly paralleling the coastline before extending offshore. Together with the El Pilar Fault farther east and related splays beneath the Caribbean Sea, these structures form an integrated plate boundary system spanning approximately 800 miles, or about 1,300 kilometers. Movement across this boundary averages roughly 3/4 of an inch each year, or about 20 millimeters annually. Although that motion proceeds too slowly to observe directly without precise instruments, its cumulative effect over centuries becomes enormous. A century of uninterrupted plate motion represents approximately 6½ feet, or 2 meters, of relative displacement. If portions of the fault remain locked during that period, much of that motion is temporarily stored as elastic strain within surrounding rocks, until an earthquake abruptly releases part of the accumulated energy. That long-term accumulation explains why major earthquakes continue occurring even after previous destructive events. Faults do not exhaust their capacity for future movement following a single rupture. Instead, tectonic forces continue acting every day, gradually rebuilding stress throughout the plate boundary. Another important characteristic of the June 24 mainshock was its shallow hypocentral depth of approximately 6¼ miles, or 10 kilometers. Shallow earthquakes generally produce stronger surface shaking because seismic waves travel a shorter distance before reaching populated areas. Less energy is lost along the way compared with deeper earthquakes, allowing more intense ground motion to reach buildings and infrastructure. The strike-slip mechanism also influences the distribution of shaking. Energy radiates outward along the rupture, often producing elongated patterns of stronger motion aligned with the direction of fault propagation. Communities situated well beyond the epicenter may therefore experience substantial shaking if they lie along the path of rupture or within areas where seismic waves are amplified by local geological conditions. Although earthquake locations are commonly represented as single symbols on regional maps, the actual rupture extends across a much larger area. For an earthquake approaching magnitude 7.5, the fault surface involved commonly measures around 93 miles in length and approximately 12 miles in width, equivalent to roughly 150 kilometers by 20 kilometers. Within that zone, rocks on opposite sides of the fault can shift several feet relative to one another in only a matter of seconds. This broader perspective helps explain why earthquakes of similar magnitude may affect large geographic regions simultaneously. Strong shaking is generated not only near the point where rupture begins but across the entire length of the moving fault. The June 24th sequence therefore represented movement distributed across a significant portion of the regional plate boundary, rather than activity confined to a single point beneath the surface.